All right. Hello, hello. Hey, class. How you guys doing? Who's here? Anybody here? I've got a special present for anybody who is already here, and that is to see my new dog. Just got adopted this dog yesterday, and his name is Rigel, and he's a sweet little doggo. And if nobody's watching, I'm going to clip out this part in the YouTube so that only the people that show up on time can see. I'm just kidding. Probably won't do that. But hopefully some of you are here. Please say hello if you are. Hi, Flannery. Thank you. So we just sort of adopted or rescued the dog. It apparently um, had been found in the woods, just given a little bit of feed every now and then wherever it was, and then been feeding it back up to a healthy size, and so it's about 1.5 years old. It's some sort of mix between a Great Pyrenees and some sort of Labrador and or Retriever. So we're excited. My wife and I both had dogs growing up, but never owned any as adults. So that's what's been going on with me this week. I can't bring the dog in just yet to show you because we did put up some books on our bookshelf, and he's not completely house trained yet. He slobbers a lot and don't want to mess any books up. But perhaps by the end of the class, I will bring him in to say hello for class. Anyway, today I figured we ought to go through the exam 2 solutions. I have not started grading, but this will give me a good template when I walk you through them and we write all the solutions out. I think that'll end up helping me to with the grading process. So that's currently my plan. It would help if I plugged in my writing pad. So we'll go through the exam solutions, and I will begin grading them probably this afternoon, or if not that, then tomorrow. And hopefully next week I'll have the grades back for you based on kind of what we're looking at today. All right. Oops. So let's get this guy out of the way a little bit. Okay, so for the exam, I think let me just take a quick look at my PowerPoints. Yeah. Okay. As I mentioned last time, we have kind of the partial credit system. Hopefully, you got an appreciation for how that went last time. And one thing I will say, keep in mind that when I'm making these exams for the online system, I really have to make them more challenging than perhaps I should, or than perhaps is ideal. And the reason I have to do that is because it's the online format. Unless I'm going to sit here and monitor each of your webcams and be invasive that way and track, go through all these hurdles to track all of that stuff, then I'm not sure that, those of you who aren't in it to learn are going to just go and Google the same question I used maybe 5 years ago or whatever and find it and use the solutions there. So rather than do that, I make new questions or revise old questions so that that's not really a possibility. So at the end result, these are probably more challenging as a whole than I would have liked. However, that does mean I'm going to be very generous with partial credit, especially on problem 3. You'll see is probably more involved than is ideal. And that means maybe some of you got caught up and spent too much time on that problem. And so again, I'm going to be gauging my grading based on how much I've seen that you've been able to show me that you learned. I understand that by the time you got to problem 4 and it was a little bit different feeling than what you've seen, you'll see today that it actually is a very straightforward problem, but I will be sympathetic that by the end of the exam that would have felt perhaps more difficult and maybe even felt unfair in a way for me to ask that particular type of problem. So just bear in mind that I am going to be generous with partial credit. I think you probably saw that on the first exam. And so really what I want to do is measure the level of learning, not so much the performance or anything like that. Okay, so with that, feel free to stop me with any questions, pull up your exam files that you submitted, and let's dive into it. So problem 1 said in order to keep a set of 3 Olympic swimming pools clean, several granular filtration cartridge units are used. Each unit is cylindrical with a 1.25 meter diameter and 1.5 meter height. So perhaps the best thing to do before anything else is to go ahead and draw these cylinders. Not the best drawings here, but we'll get there. So these granular filtration units are going to essentially have be treating, I'm sorry, it's just really 3 swimming pools and an unknown number of cylinders, right? So we have 3 pools, not drawn to scale, and we're treating the water from each of these, and each of these guys are 1.5 meters high, and then the diameter is 1.25. Okay, and then each pool contains 2.5 million liters of water, which is times 10 to the 6th liters. And that's each of them, right? So then the total volume. And I'm just writing stuff out here before I even look at what we are actually solving, just in case we need this type of information. I would encourage you to do the same when you're solving problems, but be thinking about, what you might need, and then check the problem prompt to see, okay, what do you really need? But simple things like this, you can do 2.5 times 3 gives you 7.5 million liters. Okay, so then the problem goes on and says each pool contains, that much water, and the filters must treat enough water such that the hydraulic residence time is 1 day for each pool. And so what that is saying is the filtered water is recirculating, so it's recirculating back into the pool. So each of these must treat and recirculate essentially, so however many filters we have, the total number of filters must recirculate 7.5 million liters per day. So we said theta equals 1 day, and we know that that's equal to V over Q, and so we can solve for Q and say Q is going to be 1 day divided by our volume, so that is 1 divided by 7.5 times 10 to the 6 liters, and this is 1 day on top. So if we do that, we should end up with, and I did something backwards. Hang on, let me back up. Okay, our theta is 1 day. Theta is volume over flow rate. We want to solve for flow rate, so Q is going to equal, if we put that over there, it's going to be the volume divided by theta, which is going to be 7.5 times 10 to the 6 liters every day. which makes sense because it said, we're talking about that hydraulic residence time. We want basically to do a full water change every day. Okay, so then we have, it talks about how the filters are pressurized and they're operated at this high rate of 15 meters per hour. So that operated at, that gives us a hint that we're talking about a loading rate, VA, 15 meters per hour during filtration and 25 meters per hour during backwash. So we could say V backwash equals 25. Okay, the filters automatically backwash and rinse after 24 hours of filtration time, taking 15 minutes for each process. So the T backwash equals 15 minutes. And the time for the rinse is also 15 minutes. It doesn't mention anything about air purging, so we can assume there is no air purge. And I think that in a pressurized cylinder type thing, it's probably not common to do air purging. And perhaps less necessary. I'm not sure about the necessity, but you probably don't want air bubbles in a pressurized system because that might mess with the system in some sense. But I don't know. Okay, so those are the things we have. We also know that the total cycle time is 24 hours. Okay, so part A says what is the effective loading rate of the filters, and I wanted it in meters per hour to 1 decimal place. So we need to find our effective, and we have an equation for that if we recall. And let's just make sure I get this right. If we go to our equation sheet, here it's going to be our effective loading rate, that's the volume filtered minus volume backwash minus volume rinsed, divided by the area of a filter times the cycle time. The total cycle time. So volume filtered minus volume backwash, volume rinsed. Okay, so that's our equation, and then we need to basically find each of these volumes, and then we can solve. I guess we ought to go ahead and say our area is going to be, the area of the filter in that bed is going to be pi over 4 times diameter squared. It's just pi r squared, but we use diameter instead, so diameter is 1/2 of a diameter is 1 radius, and so 1/2 squared is 1/4, which is why we get the 4 there. So the area of each of these then would be, and let me get to this point on my Excel sheet, area would be 1.23 square meters. Okay. So then with that, we have the volume, we can say is going to be that the speed at which the water is flowing through. So that's going to be our loading rate. So VA times the area of the filter. That's going to change it from a speed to a flux. So meters per second to cubic meters per second here, and then multiply that by the time of filtration. So it turns out we need to find the time of filtration as well because we have everything but that. So with our time of backwash and time of rinse being 15 minutes each, that means that the time of filtration should be 24 hours minus 30 minutes. So we can just say 23.5 hours. Okay, so then there's a question about, well, what units are we in? Our loading rates were given in hours, so we'll stick with hours there. And we'll say that these guys, the 15 minutes, we could just even rewrite them as 0.25 hours. Because 15 minutes is a quarter of an hour. So we'll go ahead and do that. Okay. All right, then it should be pretty simple and straightforward to find each of these. Of course, for the backwash, we have a different loading rate. Our backwash, here the filter, time there, and our rinse is going to use the same loading rate. Okay, so with that, we should get a volume for the filtration. Volume for the filtration should have been for 1, we'll round that to 2 cubic meters. The volume for the backwash then would be 7.7 cubic meters, and the volume for the rinse would be 4.6 cubic meters. Okay. So with that, then we are pretty much ready to solve at that point for our effective loading rate, because now we have each of those components, and we can just put in those numbers and we'll find that our effective loading rate is actually 14.3 cubic meters per hour per square meter. So we'll write that as meters per hour. And if we check this number should be less than the loading rate, and at least by a little bit, and that's exactly what we see. So that's good, and that's our final answer for part A. So hopefully that makes sense. Part B asks how many of these filtration units are required in order to keep the pools clean by the standards that were given. And I ask you to answer any whole number because it would not make sense to make half a filter. You're manufacturing these systems, you might as well not try to make 4 and then one that's half the size of the others. That doesn't really make as much sense. So you would make 5 instead of 4.5, right? Okay, so with that, this is going to be a relatively simple process. Here we have the total flow rate that we have to treat is 7.5 million liters per day, right? That's our Q total. We can rewrite that. Instead of in liters, we can write that in cubic meters and say that 7,500 cubic meters per day. And then we could also put, if we needed to, we could convert that into hours, cubic meters per hour, by dividing that by 24. But essentially what we want to do, and what we really need to check is what's the effective flow rate provided by one filter. And then we can say that apply that to however many filters we need in order to get this, this flow rate. So we can divide this number by essentially, and you know what, let's go ahead and convert it to hours. Let's go ahead and say that is going to be equal to some amount of cubic meters per hour. I think I probably have that here. Yeah, that's going to be 312.5 cubic meters per hour. So then what we can say is, let's take this and say 312.5 cubic meters per hour, and then divide it by the effective flow rate provided by one single filter. And the effective flow rate by one single filter is going to be the loading rate, the effective loading rate for one filter, times the area of that filter, because that will give us, so that's going to give us a cubic meters per hour on top, and then on the down below, this is going to be our effective is meters per hour, and this is going to be cubic meters, so it's going to be cubic meters per hour on the bottom. So total, this is total flow, and then divided by effective flow times one, we're just going to use the, in terms of units, this is times one filter, because what we really have here is square meters per filter. That's probably the best way to look at it. So the area is some number of square meters per filter, and so this is going to be the effective flow per filter. And so filter as a unit is going to come up onto the top when we divide the flow rate. So that's going to be cubic meters per hour divided by cubic meters per hour, and times, divided by the filter, or the number of filters here. So that's just how I'm working it here. So that means then this number is going to be, it will be 17.82, which means we need a whole number of 18 filters. Okay, and then the final, I guess that might not be, that's not the final, but part C asks what is the filter efficiency of these filters, and what this is really referring to is kind of how efficient are they, that efficiency term, in terms of the amount of water used versus how much water is recovered, right? So the filter efficiency is going to be, and I'm sorry, that was a bad drawing there, right? So nu is going to be, and this is the volume filtered minus the volume backwash minus the volume rinsed divided by the, the total volume, right, the volume filtered. Yeah. So we already have all these parameters, so that becomes very easy. We just need to go and plug them in. And then, if it's asking as a percent, we can multiply by 100%. So with that, we can get our filter efficiency as 97.2%. So for this water, for the swimming pool water, what this means is we're essentially, we're getting 97% of that 7.5 million liters across all the pools. 97.2% of that will remain in the pools. We can recycle that amount of water, and then we're essentially going to have to add fresh water, new water, for that 3% or 2.8%. So as we're operating these swimming pools, we have to add some amount of water every day from the tap or whatever, so that we maintain this amount of water, because when we backwash those filters using this pool water, we need to send that water, that backwash water, out into a waste collection system, probably to the sewer, because it's not going to be suitable to go back into the pool. Okay, so then part D asks, well, during the off season, the pools are used less frequently, and the operators find that a lower hydraulic residence time can be used to keep them clean. So our theta is going to be lower, right? So theta new is essentially less than 1 day. And so the question is, how many filters would be needed if the recirculation flow was reduced to provide a residence time of 3 days? I'm sorry, I meant higher. So essentially the water is staying there for longer, right? So in this case, we're going to say this new theta is 3 days. Okay, so then really we're just going to repeat the same process from earlier, except instead of having our flow rate, our Q total last time was 7.5 million gallons or million liters per day. This time the Q total is really going to be 3 times smaller. So it's actually going to be as if we're just doing one swimming pool. So that's going to be 2.5 liters per million liters per day, right? So 2.5 times 10 to the 6 liters per day, which is 2,500 cubic meters per day. And this is going to be, if we divide that by 24, that's what, going to be just over 100 cubic meters per hour. And so we can convert that, and yeah, that's going to be 104 with some change cubic meters per hour. And then we really just repeat the same thing we did earlier, right? We have that number, 104.2 cubic meters per hour, and then our effective loading rate didn't change. We just changed the hydraulic retention time. So then that's going to be divided by our effective loading rate times the area per filter, right? And then that's going to end up giving us a number 5.94, which again we need to round to here 6 filters. Okay, so I didn't hear too many complaints about this problem, so hopefully that all makes sense. Problem 2 was a membrane filtration problem, and here we have a filtration unit for treating water in rural areas that lack major infrastructure. Gravity is used to drive water through a 0.22 micron membrane, and this is kind of setting up similar to what we talked about with gravity-fed membranes. So the membrane unit houses 22 square meters of membrane area. The membrane system is operated in a cross-flow regime under a constant flux to meet, so cross-flow, constant flux regime, to meet a demand of 500 liters per hour of water. The treated water is 300 degrees Celsius, and then I say note that the pressure of 1 meter of water is equivalent to 9.8 kilopascals. So part A asks, what is the flux across the membrane given the parameters provided? And I ask you to answer in meters per hour to 3 decimal places. Okay, so the flux across the membrane, sometimes we call that J. We have a few ways to know this, and if we take a look again at our equation sheet, we can take a look and we have J is related to the transmembrane pressure divided by the resistance times the viscosity, but we also know that it can be a little simpler, right? We also know that it's Q over area, just like our loading rates. It's a flow through some area. So even though we have pressure and it looks like maybe we have enough information to use that other equation, we also, you can take the simpler version and say, well, we also know that we were told we need 500 liters per hour of water, and we had 22 square meters of membrane surface area. So to get that into like terms here, we can say that's 0.5 cubic meters per hour divided by 22 square meters. And that will give us an answer in meters per hour. So let me get to that part of my Excel sheet over here. So then our answer then is going to be, for our flux, is going to be 0.023 meters per hour. Or you could say cubic meters per square meter per hour, but this is what I asked for. So that was actually quite simple. We're just looking at the amount of flow that was demanded by the system. It's operating so that it meets that constant flux. And we had some information about the area. So the flux has to be that amount. Part B says if the recovery rate of the membrane is 95%, so that's the water recovery, how much water must be fed to the membrane unit? So Q feed, if we're, again, you can make a diagram, and let's do it vertically just because we have a membrane system that is set up this way, where we have Q feed. This is what we're asking for here. We know that the Q permeate is 500 liters per hour, because we were given that in the initial prompt. And we know it's cross flow, so there's also going to be some sort of, if we draw it this way, we also have some sort of Q retained, right? Okay, so for our recovery rate, we know that essentially 95% of the water comes out our permeate, and that means 5% goes to waste. That means we really need 5% more than 500 liters per hour in order to find this relation. And we can again go back to our equation sheet and use this recovery rate, lowercase r, QP over Q feed. We know the recovery rate is 0.95, and then we can solve for QP because we know, or Q feed because we know QP. Okay, so R equals QP over Q feed, which is equal to 0.95. And so our Q feed is equal to 500 liters per hour divided by 0.95. And just by taking a look, that should be, it's kind of like multiplying it by 1.05. So that should be probably 525 or something near that. Okay, and the correct answer is 526, 0.3 liters per hour. Back to part A real quick, yes. Part A was just simply getting the flux based on the flow that we know it was producing divided by the area with which it could produce it. So the flow rate here, that was the constant flux that was demanded that we require the membranes to produce. Yeah, no problem. And sorry, I might be slightly slow to answer questions right now because I'm using both screens. One of them, sometimes I don't have my my overlay set up in front of me. I suppose maybe I should get a third monitor for that if I want. Okay, part C asks, when the membrane is clean, the membrane resistance is 1.8 times 10 to the third per meter. How many meters of water are required to pressurize the membrane to yield 500 liters per hour of water? Answer in meters to 2 decimal places. So what this is asking is essentially how much pressure. What is the transmembrane pressure that must be applied? And so the potential confusion here is recognizing that we're using the height of the water that's stacking up above the membrane in order to drive the water through it. That's going to be our source of pressure. Remember, if you were to dive deep in the ocean, the pressure becomes enormous, and in terms of engineering and exploration, you have to account for that pressure in order to survive or to be able to work in deep places in the ocean. So that's what we're talking about, is how many meters of water above the membrane are required. Just like our granular filters, we can use that stacking of water higher and higher to increase the pressure to meet the demand. So if we are feeding the membrane a constant amount of water, that 526 cubic meters, or excuse me, liters per hour, then, and it's driving it through to get 500 liters per hour, then it will automatically, you'll end up stacking more water on top to keep a constant flux going through. It will just increase the pressure over time by adding more water on top of that membrane. So we need to remember that this part that was given, 1 meter equals 9.8 kilopascals, because we need to work in pascals for our transmembrane pressure. And to answer the question, we need to get a transmembrane pressure and then convert it to meters of water. That's our strategy here, is to find what it takes transmembrane pressure wise, and then convert that from the pascals into kilopascals into meters in order to know how many meters of water. So our flux we looked at a minute ago, this is transmembrane pressure. Now that we have something about the resistance divided by the total resistance of the membrane times the dynamic viscosity of water at that given temperature. So we know R of T based on the 30 degrees of water. We know that our mu is going to be essentially 7.98 times 10 to the minus fourth kilograms per meter per second. And it might have said 0.798 times 10 to the minus third. Either way, just don't forget that to look at the units when you do that part. So with that, we can say, well, we know our flux. Our flux is 500 liters per hour. We probably need to put that into cubic meters because our other parameters have seconds and meters. So we really should put this into cubic meters per second. So right now this is 0.5 cubic meters per hour, which is equal to, if I have it, okay, and I might, okay, there, let's see, yeah, there we go. And so this is going to be equal to 6.31 times 10 to the minus 6 cubic meters per second. And that's because we divide 0.5 by 3600. I think that might be off. That looks off to me. Yeah, I think in my calculations, for some reason I was not using 500. Oh, that's flow rate. I'm silly. I should have been using the flux. Let's see if you guys caught it first. No. Okay, so what happened here was this is a flow rate, not a flux, and that's not what I should be using, right? What I should be using is the actual flux. The flux is what we calculated a minute ago. We know the flux with given 500 liters per hour, given the amount of membrane area, we calculated the flux to be that 0.0227 or 0.0023 meters per hour. And so if we translate that into seconds from, and that should be meters, not cubic meters. If we divide that by 3,600, then we get 6.13 times 10 to the minus 6 meters per second. That's our flux in meters per second. And we need to do that because our other units are in meters and seconds. And if we take a look at pascals, that is also a derivation based on kilograms, meters, and seconds. Okay, so that's our flux term that we can use, and then we can set this equal to the amount of pressure that we are solving for divided by that 1.8 times 10 to the 13 per meter times that 7.89 times 10 to the minus 4th kilograms per meter second. And so at the end of the day, our transmembrane pressure should be 9.07 times 10 to the 4. And that's pascals, or 90.7 kilopascals. And so then we divide that by 9.8. So 9.8 kilopascals per meter. So essentially the meters of water is going to equal 9.25. So that much water stacked on top of that membrane. Okay, so that is really a membrane problem with just a little extra flavor about using that conversion from pressure to meters. And by the way, one of the reasons I ask this and have this question for you is actually because during my graduate work, I went and toured a wastewater treatment plant, and somebody mentioned that I was studying environmental engineering, and the operator asked me, like, oh, okay, you're an engineer, you must know the answer to this question. And he said, how many feet is a gallon of water, or something along those lines? Really just asking this concept, how much pressure, I think it was how many feet is 1 psi? And it just sort of, I wasn't understanding the context because I really actually hadn't thought about things practically in this way, but it's a very common hydrology type of problem and situation. He was talking about the amount of head or pressure applied by something like that. Well, I have to admit my undergraduate degree was not engineering, and I actually missed out on some of the core hydrology type of stuff. I had a more earth and atmospheric science type stuff. So I probably should have known, but it just, my mind blanked, and I wasn't actually able to answer him in front of the people that were expecting me to. It was kind of funny. But anyway, there's some ratio that you might know, and you probably expect if you're an operator and you're dealing with these things all the time, then it's probably just common knowledge, kind of at the tip of your mind all the time, because you use it so often. So this was a problem that you should have been able to solve, but it just had that little twist in terms of the way we're talking about pressure. Okay, so during operation, the membrane fouls continuously such that 5 times 10 to the 12th per meter resistance is added every 20 minutes. How many meters of water will be required to supply that same flow rate after 1 hour of operation? answer in meters to 2 decimal places. So really what I'm saying is our total resistance is just going to be equal to the resistance we started with, which was 1.8 times 10 to the 13th, plus some amount of added fouling resistance. And I said it adds every 20 minutes, and then I ask about after 1 hour. So it's really just 3 times 5 times 10 to the 12th. So it's really 1.8 plus 1.5 times 10 to the 13th. So what we'll see is the new resistance should be 1.8 plus 1.5 is 3.3 times 10 to the 13th per meter. And then we solve the problem again. So we just have to go back to right here where we put in the resistance, and we know the viscosity, and we know the flux had to stay constant, and so then we just need a new value. So I'm gonna, for the sake of time, I'm just gonna go ahead and give you that answer here. And it turns out that this new height is essentially, let's see, it asked in 2 decimal places. This is going to be 16.96. So we can see that, in this case, if we are imagining the fouling is occurring in the way that was described, then after an hour of operation, we went from about 9 meters of water to about 17. So kind of gives you some reference point, and then maybe you backwash and you're back down to 9 meters. Okay, so hopefully that makes sense. I'm going to move on to the next question. I'm happy to come back, answer any questions you do have. Problem 3 was really a disinfection and chlorination type of problem, so we need a bit of chemistry here. And essentially what we were looking at is some of the difference between chlorination and bromination. So part A, so we've got this problem and we say bromine and chlorine are very similar, both active forms of a kind of chemical disinfectant, and they both can be used to treat recreational water, so like a swimming pool. Let's consider a simple case of a 15 cubic meter pool. Typically, there's no meaningful flow in or out, and it's well mixed. So it's acting like a batch reactor, right? So we had to decide on what type. It's well mixed, and it's got water in it. There's no flow rates coming in or out. It's a batch reactor. And we're making it a little bit simpler and saying that inactivation by OCl minus and OBr minus are always negligible. Great. So that means maybe we have a lot of it, but we're not really counting that towards the inactivation credit. The following table provides constants for disinfection of resistant cyst-forming pathogens, something like Cryptosporidium that makes that cyst shell and it's hard to kill. So what mass of calcium hypochlorite, so essentially bleach but with calcium instead of sodium hypochlorite, you've got OCl2. How much of that must be added to the swimming pool to achieve a total chlorine concentration of 5 milligrams per liter? And I ask you to answer in grams to 1 decimal place. Okay, so in order to take a look at this, really what we're talking about is total chlorine is really total OCl plus HOCl, okay? And what I'm going to do is I'm going to say that we can probably, these are, if in terms of molecular weights, we'll say molecular weight of OCl minus is 51.45 grams per mole, and molecular weight of HOCl is equal to 52.45 grams per mole. Okay, so then how much mass of this do we need to add in order to get 5 milligrams per liter? Well, what we can do is take the molecular weight of the CaOCl2. That's going to be, let me look it up, we've got 142.98. Grams per mole. And anytime we're adding that, the addition, so 1 mole CaOCl2, that's going to be giving us 2 moles of OCl minus, right? Because that's going to be, when it dissolves, we'll get 2 of those OCl minus. So what we need to know then is we're essentially going to back calculate from the mass here that gives us the moles there to give us the moles here to give us, and then back up one more step and get the mass here. So that's the process here, and we're going to do that for a 15 cubic meter pool. So our volume is 15 cubic meters, which is 15,000 liters. And so, at the end of the day, we need 5 milligrams per every 1 liter. So we can say from the start, okay, well, that times 1,500 liters equals some amount of mass of OCl that we need. So milligrams of essentially OCl, and we can keep it as OCl. That it's simple enough, those are close enough, and we're not given any information yet about the pH, so it just makes sense to keep it that way. Okay, so given that, we can say that our, let's see, well, 5 times this 15,000, I mean, I guess that's just, what, 75, 75,000 milligrams that we need. And then we can convert that to grams, so 75 grams of OCl needed, and we can go from there and say that's going to be, if we take 75 and divide it by our 51.45 grams per mole, that's going to give us 1 point something moles, moles per liter. Actually, that's just moles, yeah. And then, actually the way I solved it in my Excel sheet is I left it as a concentration, and so I didn't do this step yet. So I've got the wrong numbers in front of me, so just give me 1 second and I'll straighten this out. So let's go ahead and just do it the way I did it in Excel, so that way I have all the numbers in. You can do it either way, and you just need to count for the total volume at some point. And as you'll see right now, what I'm going to do instead of calculate it right now, I'm going to go ahead and put this into moles per liter units. So 0.005 grams per liter, and then we divide this guy by 51.45 grams per mole. That will give us a chlorine concentration in terms of OCl minus that is, that's required, and that's going to be 9.72 times 10 to the minus fifth, I think, moles per liter. Yeah. Okay, so then we have that many moles per liter, and in a minute we will convert back with the 1500 liters. Like I said, you can do it before or after, it doesn't really matter. Since I did it this way in my Excel sheet, we're going to continue this way. Okay, so from here, that means that we need half that many moles of calcium hypochlorite. So we can say multiplied by 1 mole OCl minus per 2 moles CaCO3, which then should give us some number of calcium chloride, which is 4.86 times 10 to the minus fifth. Moles per liter of CaOCl2. From here, then we can convert to mass. So mass of CaCOCl is going to be equal to 0.0069 grams per liter. Then we multiply by the amount of liters, and we get a final mass of 104.2 grams. So as you see here, I went from moles per liter, I just multiplied by the grams per mole to get that into grams per liter, and then from there I multiplied by the volume of the swimming pool, 1500 liters, to get our total mass you have to add. So if you think about it, 1 kilogram is like 2.2 pounds. So 100 grams is like maybe a quarter of 1 pound, just as kind of a thought process there. So not a lot of the chlorine to achieve that 5 milligrams per liter. Okay, so then that's part A. Part B says how much CaOCl2 must be added to the pool in order to achieve a 3-log reduction of the pathogens at pH 7 in 1 hour. And I ask you to answer in grams to 1 decimal place. So I copied this table here for our use. So really what we're looking at is in a batch reactor, we have N over N naught equals e to the negative kCt, because we've got our Chick-Watson kinetics. We are given the k here. So we say, and we know that N over N naught is 3 log reduction, so this is like 1 over 1,000 or 0.001 equals e to the minus k, which is, in this case for OCl, that's going to be 0.123. So 0.123 liters per milligram minute. And notice here this is per milligram, so that means we're looking at milligrams of chlorine, so milligrams per liter of chlorine, times our time, which is 1 hour. This is in minutes, so I'm just going to convert that hour into minutes and say times 60 minutes. So right away, I've just documented essentially everything we need so that we can understand what we're missing. And that what we're missing here is that concentration times concentration of HOCl, because that's the one that's doing the disinfection. Okay, so we could rearrange and say natural log of 0.001 equals negative 0.123 liters per milligram a minute times 60 minutes. times the concentration of HOCl in milligrams per liter. So C equals, and I'm just gonna write it all out so we have it here, 0.001 divided by negative 0.123 times 60. That's going to be our answer. We just need to find, we can plug in those numbers and then we'll find our answer here, but we also need, so that's going to be our answer in terms of HOCl in milligrams per liter, and then we need to see how much mass we need to add to the pool like we just did in order to get that much HOCl at pH 7. Okay, so let's start on that. So the C here, if we put those numbers in, that C should be 0.936 milligrams per liter. We can then say that's going to be, so milligrams HOCl per liter, and we can find what concentration that corresponds to in moles per liter by dividing, well, first of all, converting that to grams per liter, divide by 1,000, and then convert that grams per liter to moles per liter by using the molecular weight, which we said a minute ago was 52.45. And so we can get this HOCl, this is going to be 1.78 times 10 to the minus fifth moles per liter. And so here we have now a way to convert from the, or now we have the moles per liter of this stuff, and so we can use our equilibrium equation dealing with pH to find how much total chlorine we need in the system. You know, part A kind of primed us and showed us how to convert from a mass added to the swimming pool into the effective milligrams or grams per liter that you'll have in the swimming pool. And so that's kind of where we're heading with this part. So here we can say our Ka is equal to, and we've got the value up here, 2.88 times 10 to the minus 8 is going to be equal to H plus times OCl minus divided by HOCl. So right now we've got everything, we've got HOCl that we need, we've got H plus, and what we want to know is how much OCl minus is in there in addition to the HOCl at pH 7. So all we need to do then is solve OCl minus and say that that's going to be equal to 2.88 times 10 to the minus 8, and then divide that by 10 to the minus 7th for the hydrogen, and multiply the HOCl, which is 1.78 times 10 to the minus 5th moles per liter for the HOCl. Then we can get a value here. That value is going to be 5.14 times 10 to the minus 6 moles per liter, which means the total chlorine, so I'll just say OCl total, is going to be essentially this number plus this number. So that'll end up giving us 2.30 times 10 to the minus 5th moles per liter of chlorine in general. From there, we do the exact same process we did for part A to get back how many grams do we need to add. And I'm going to skip ahead a little bit and just say, let's say repeat part A process, and we're most of the way through it already. Because given it in this form makes it easier to solve for the mass. So we don't have to do the whole part A process, but just the last part of it. And then we will end up with a mass here of 24.7 grams. Okay. So hopefully that makes sense. So here again, we're just going to convert from that using the molecular weight of chlorine. To get the mass of chlorine, you have to mass of the calcium, the CaOCl2, and to get the mass of that, we add. Okay, part C then asks how much sodium hyperbromide, NaOBr, must be added to the pool in order to achieve a 3-log reduction of pathogens. So it's really the same question as part B. Except that we're using the different species. We use a different value here and a different value here. That's going to essentially shift the equilibrium. So if we remember for the Ka for chlorine, it essentially means that you have equal amounts of HOCl and OCl minus at pH 7.54 or thereabouts. And just, I wrote it, slightly different here, but essentially at 7.5 pH, they're approximately equal. So at 7 pH, you maybe have 60 or 70% of your chlorine is in the reactive form. Now it turns out that for the bromide case, this pKa is higher. So it's like pH 8 to 9 range is where you get equal amounts. So even though we have a slower reaction here, a smaller number for the reaction rate, we're going to end up with more HOBr compared to OBr minus. So less wasted bromine in that sense. So otherwise, it's the same problem, same as part A with different numbers. Different constants, but you just repeat that process. And so I'm going to skip ahead because we're low on time. And what you'll find is that the mass you have to add is going to be 221.6 grams. Now, of course, your molecular weights are different, these constants are different, so there's different elements here, but overall it's the exact same process that you'll need to take. Okay, so somebody's saying for part B, you got 5.13 times 10 to the minus 6 moles per liter for OCl minus. And you're talking about for OCl minus when you're solving here. So 5.14 versus 5.13 versus 5.14. Yeah, that's just a rounding difference. That's no big deal. Okay, cool. Okay, and if there are special concerns or issues here, I'll be glad to help you with them. And again, as I said at the beginning, this is probably more involved than it should have been for your exam, but it will show me what you learned and how you were approaching the problem. And so I'm going to be generous with partial credit there based on what I see that you've learned rather than how in fact you've performed on the problem. Okay, so problem 4, our last problem says, let's consider a portable UV disinfection system used for 1 liter bottles of water. The system consists of one battery-powered UV LED, which emits light at 278 nanometers. The coefficient of specific lethality for the inactivation of E. coli by this wavelength is 0.675 centimeters squared per millijoule. If the LED emits 0.2 milliwatts per centimeter squared of light, how long will it take to cause a 3-log reduction in E. coli population in the 1-liter bottle? And then I give you a kind of a reminder and a hint that 1 watt is 1 joule per second. So joule per second. And then I ask you to answer in seconds to 1 decimal place. So a 1-liter bottle of water, this is going to be essentially a batch reactor. And if you think about a water bottle, you know that it's pretty well mixed just by your activity, moving it around. It's going to be pretty easy to have that pretty close to an ideal batch reactor. Okay, so that's our system. So that means our 3-log reduction, n over n naught, 0.001, that's going to be in the context of a batch reactor, meaning we can establish this as e to the minus k times t, where k is the overall reaction rate constant for the system. Now, I'm writing it this way to remind you of the general principle of how we're going to solve the reaction. Now, obviously, the problem has different stuff in it. It has this coefficient of specific lethality and some amount of light that's being emitted. So what I'm wanting to do is draw your attention to the units here. And I gave you that hint in hopes that that would help you to do so. So if you remember the germicidal intensity stuff, it was a lot like the Chick-Watson kinetics. So we could write this as like a K star. So where K star in the Chick-Watson was a K times C. And in this case, we're going to say this is a K times the germicidal intensity that is delivered at some wavelength. So it's really the same concept here. So if we take a look, let's say we need the K star, and we know that the specific lethality, this K here, that's 6.75 centimeters squared per millijoule. Okay, the other thing I want to recognize here is the K star, in this case, should end up in 1 over time units, right? This has to be 1 over time because the K star has to be 1 over time because you're multiplying it by time, and it has to be unitless in the exponent. So if that has to be unitless, and that's essentially the structure that we're going to use, then this K times the intensity should leave us with just simply per time. So let's see if we can make sense of that. And I wrote this incorrect, 0.675. Okay, so this is centimeters squared per millijoule. Now, if we multiply this by that intensity that is being emitted, that 0.20 milliwatts per centimeter squared. If we take a look at those units, the milliwatts we can rewrite as millijoules per second, because 1 watt is 1 joule per second, 1 milliwatt is equal to 1 millijoule per second. So with that, we actually have very convenient units. So I'm just going to go ahead and rewrite this guy as millijoules, and I'm going to put seconds on the bottom. So millijoules per second instead of watts per centimeter. And so if we look, this will cancel. The millijoules cancel, the centimeters cancel, and we're left with per second. So K star then is going to be equal to that multiplication, 0.675 times 0.2, and I think I've got that number. Let me find it in my Excel sheet. That's going to be 0.135 seconds to the minus 1. Okay, so that is essentially it from here, you've done this a million times. So that was the only complicating factor. And it was something that I know you didn't have a lot of direct practice with, but I had introduced the concept, and this was really just a units problem where you were given this reminder what a watt is in terms of units. So I was hoping, and I know some of you felt very uncomfortable with this problem, especially after the previous problem. I will be sympathetic. Again, I'm going to give you partial credit where I see it's fit. But at this point, you're just solving for, let's see, what was the question asking? How long will it take? You're just solving for time. So we're just going to say the natural log of 0.001 equals minus k star times time. And I ask you to answer in seconds to one decimal place. And so when you solve this with k star there, the amount of time should be 51.2 seconds. Okay, so as I mentioned, it turns out that it is a simple problem after you get past the units here, because it's just dose. It's just an issue of dose per time, right? How much influence of that stuff are you getting? Okay, so then part B is a follow-up, and it says, okay, when the battery is nearly out of energy, it's almost run out, the power output becomes 0.05 milliwatts per centimeter squared. Now, how long will it take? Well, that's a simple matter of changing our K star. So last time we had 0.2 milliwatts per centimeter squared. This time we have less, and it gives us a new K star of 0.03375 if we were to take it all the way out per seconds. And so now the time, same process, the time becomes 204.7 if we're doing to one decimal place. And you could have just simply looked and said, well, our intensity dropped by a factor of 4, so we expect that the amount of time should increase by approximately a factor of 4, and which it did, right? So 51.2 times 4 is around 204.87, somewhere in there. So that's the final problem. And again, I understand there were some people who felt like this problem was out of the context, but I have been harping on you all semester about doing your units, looking at your units, and I gave you this tip about the units. So I hope that some of you got it. Okay, with that, that's all I've got. I will begin grading them, your exams, shortly. And after I do so, of course, happy to go back over issues that may have come up. All right, so thank you for those of you who tuned in today. I'll pick up on Tuesday, and we'll talk about essentially how biological oxygen demand occurs and decays in natural systems after discharge from wastewater treatment. All right, I will see you next week. Have a good weekend.